What is epigenetics? Monkey has a manual. The manual has all the instructions, but the monkey doesn't use every page. And here's the weird part. Two monkeys with the exact same manual can end up very different. Think about it like this. DNA is the instruction manual of the cell. Every cell in your body has the full manual, complete. But if every cell has the same manual, why does one cell become a neuron, another become a pancreas cell, and another become skin? If everyone has the same manual, who decides which pages each cell reads? Today you're going to understand this without memorizing scary science words. There is a control layer that turns pages of the manual on and off. That is epigenetics, and the collection of those markings is called the epigenome. Epigenetics does not change the text of DNA, it changes what gets used. Now imagine two identical twin sisters, same DNA, same manual, but their lives are different. One sleeps well, exercises, lives calmly. The other is stressed, around proteins like a thread around a spool. Those proteins are called histones. If the DNA is wrapped very tightly, the cell can't read that part. If it's wrapped loosely, the cell can read it. Epigenetics, in practice, is a system that says, tighten here, loosen there, lock this page. So without overcomplicating it, what are the main mechanisms? First, DNA methylation. It's like putting a sticker on top of a gene that says, do not read this. The gene isn't gone, it's just silent. Second, histone modifications. Here you don't change the text, you change how tightly the DNA is wrapped. Tighter means less access, less activity. Looser means more access, more activity. Third, non-coding RNAs. They don't become proteins, but they help regulate genes. MicroRNAs are a good example, small messages that reduce how much of a protein gets made. Short version, epigenetics is access control for DNA, and this starts early. Very early. When an embryo is forming, cells must decide, I will become an eye, I will become muscle, I will become pancreas. Those decisions depend on epigenetic markings. That's why, during pregnancy, factors like nutrition, physical state, and chemical signals in the body can influence development. This isn't magic. It's biology controlling which pages of the manual stay open at the right time. What about the parents? Many epigenetic marks are erased early in development, but we now know that some can remain. This has led scientists to study how habits and exposures might influence future generations. Important clarification, this does not mean destiny. It means there is a regulatory layer that can carry effects, and science is still figuring out how much this applies to humans. Now comes the part that grabs everyone's attention. In an experiment, scientists trained mice to associate a smell with a shock. Later, the offspring reacted strongly to that smell, even though they were never shocked. And even the next generation showed the same sensitivity. Sounds crazy, I know, but the idea is simple. The epigenome responds to the environment and can leave biological marks. This is not conscious memory, it's regulation. So why does any of this matter? Because many diseases are not just about broken genes. Sometimes the problem is a gene in the wrong mode. In cancer, for example, genes that control cell division can become deregulated. What should stop doesn't stop. What should slow down doesn't. And this opens a huge possibility. If epigenetic marks can be reversible, we may be able to develop treatments that remove harmful marks without disrupting helpful ones. That is one of the biggest challenges. Act in the right place without breaking everything else. So remember this sentence. Genetics is the manual. Epigenetics is the highlighter, the sticky notes, and the locks that decide which pages are open or closed. The DNA can be the same, but how the body reads the DNA can change a lot. And yes, sometimes epigenetics gets really bananas. If you want, In the next video, I'll explain DNA methylation and histones with an even more visual analogy. How the cell decides what to lock and what to release.